All right, for our second night of homework from our first set of notes, we are just doing compound interest in a few applications. Now, I did not want to retype this. There's nothing like exciting happening for these problems. So I didn't want to rewrite all of this out, but you do need to know, like I will ask you, I won't tell you what n is. So you need to know these vocab words. These are the only values for n you will have. So annually means n equals 1. Semi-annually is twice a year. Quarterly interest compounds 4 times a year. Monthly 12 times a year. Daily 365. Continuously is not the same as daily. Continuously is like it says, continuously throughout the day, every day, you're collecting interest. So they should be close in value, but the continuous should always be a little bit higher than daily. Now, as you're calculating these, you shouldn't have to retype the whole thing. So here, I'll type the first one. So you should be setting this up. Even though it's just 1, I'm going to set this up so that I can just make adjustments. So it's 40 years times n is 1. So I get the first value. For the second one, I just want to change this to 2. So just go up to here, press enter, and then make that a 2. Make that a 2. There's my next answer. What if your calculator doesn't let you go up there? Some of the older calculators don't do that. Press second enter, and it will type in your previous line. And if you keep doing that, it'll type in the line before that and whatever. So, okay. So, oops. See, now I've gone too far back. So let me call up that last line. Now, what if I want to change this to something that has more than one digit? Like I want to get to 365. So on the end here, that's easy. 365, I don't overwrite anything. Here, get on the 2, and then instead of delete, do second delete for insert, and see how it's kind of flashing now. If you type in a 3, it just scooches, it'll just push this over 1. Here, let me redo that. So I hit the button once too many times. So I can press in 3 right now, and then 6, and I don't want it to overwrite this and push the 5 out, so I'm just going to arrow over and say make that 365. That was my answer for 365, right? And then the formula changes for continuously. This is P times E to the RT. So practice with your calculator, because the most common thing is like these formulas are easy, but sometimes if you haven't actually been typing them, if you're just using my answer key to like write down what the answers were, then you're going to mistype something on quiz day, and that's a silly point to lose. Okay, same idea here. We are investing $12,000. We have an interest rate given to us for number 68. It's 2.5% for T years compounded continuously. So they're giving us different values of T. So same thing. It should be 12,000 times E. Make sure you know where E is. 12,000 times E right here. Second ln sets up an exponent for you to the RT, 0.025 times 1, or however many years it is. Normally we round to 3 decimal places for the AP pre-calc exam, but we're talking about dollars and cents, so we can round to the nearest cent for all of these. All right, now what about this problem? Let Q represent a mass in grams of radioactive radium, whose half-life is about 1,600 years. The quantity of radium present after 2 years can be found using this formula. So notice they built in the half-life for us. It's T divided by the half-life. It's always 1/2 to that power. This just means if we start with 25 grams, it's going to take us 1,600 years to get down to half of that, to get down to 12.5 grams. So the first question says, determine the initial quantity, which you've got to know means initial always means when T equals 0. So find Q of 0. Now, I don't need a calculator for this because that's 25 times 1/2 to the 0 power, 0 divided by 1,600. Anything to the 0 is 1. So the initial amount was 25 grams, which makes sense. You can see that in the formula. Determine the quantity present after 1,000 years. So that's saying find Q of 1,000. So we will use a calculator for this. It's 25 times 1/2 to the 1,000 divided by 1,600. Don't find this decimal and round it. Just type it in exactly as you see it. 25 E to the 1,000 over 1,600. Round this to 3 places because we're not talking dollars and cents anymore. We're talking about grams. So 46.706 grams, approximately equal to 46.706 grams. Make sure you're in the habit of labeling everything, whether it tells you to or not. Part C says use a graphing utility to graph the function over the interval 0 to 5,000. So that is telling us how to set our window. So first let's clear out whatever's in y equals. Make sure your plots are turned off up here. So we're going to type in 25 times 1/2 raised to the x over 1,600 power. All right. And the window is supposed to be set from 0 to 5,000. And then zoom fit, which we've used a lot by now, gives me this window here. So that's all we had to do for part C. When will the quantity of radium be 0 grams? Explain. So think about this graph. We've been looking at exponential graphs for a while. They have horizontal asymptotes at 0, right? So when will the quantity be 0? Never, because this exponential graph has a horizontal asymptote of y equals 0. If this were an AP exam, write out the words horizontal asymptote. So the value of radium, it will approach 0, but it will never hit 0. So I'm going to say that. The amount of, what is this? Radium will approach 0. But never reach 0. All right. Number 77. The projected populations of Americans ages 100 and over for the years 2025 and 2060 can be modeled by this function. P is the population in thousands. T is the year. 25 represents 2025. This is actual data from our U.S. Census Bureau. So part A says use a graphing utility to graph the function. So I've kept my screenshots up here. But again, let's go ahead and graph it. So go to y equals, clear out your old equation, type this in, 31.752 times e to the, type this in carefully, 0.0486x. Because if you're missing a decimal place, if you mistype a number, you're going to get the wrong value. So, okay, so that's in there correctly. The window is 25 to 60, remember? They tell us 25 is 2025, so 60 is 2060. And then you've got to zoom fit every time you set your window differently. So that's how I got that graph. Okay, so this is done. Use the table feature to create a table of values for the same period as part A. So you're not going to be able to get the whole span, or I guess I don't know how to make it show the whole span. But this just means if you press, to get to the table, you press second graph. Now, depending on where you were last in your table, like mine is starting at 37, which is not really what I want. I could just scroll until I get where I want. But what if the window of interest is like 1,000 to 1,050? Do you really want to scroll down there? No. So here's a quick way to jump around the table. See where it says table setup here? Press second window. Normally the table start is at 0, or it'll just be wherever you left off last. So I would like it to start at 25. And then now when I press second graph, the table starts at 25, right? And one other thing about this, I would like the table to count by ones, but you can also make it count by like 0.1s. Not that we want that. We don't really want that, but see how you can kind of make the table adjust to what you need it to be, but keep that at 1 for what we're doing. Anyway, that's how I got that shot of the table. And then part 3 says, according to the model, in what year will the population exceed 300,000? So remember how to set this up. The P is the population in thousands. So I shouldn't be setting my equation equal to 300,000. I should be setting it equal to 300. And we have not gone through how to solve algebraically how to solve these exponential equations yet. And that is on purpose. If you're allowed to use a graphing calculator, there's absolutely no reason to solve this algebraically. You can just say, I'm going to solve by graphing. I've got this typed in. I'm going to put 300 over here. Now, I do have to kind of guess at the window, because if I just go on my graph, oh, wait, what? I don't have to guess at the window, because if I go on my graph, apparently the answer is going to be within this range that they gave me. But yeah, that was the window was set to 25 to 60. Okay, so we can find the intersection point, second trace, intersect. I'm getting 46.210, which is what I show in the screenshot. So the question says, in what year? So remember, 46 is 2046. So I'm going to say sometime during 2046 is when the population would hit 300,000. Okay. Oh, wait. In what year will the population exceed 300,000? So actually, let's say this. Instead of during, let's say after 2046, or you know what, it still would be during. It would just be sometime toward the end. So nope, I'm switching that back to during 2046, not in the beginning, but anytime after the 2/5 of the way through, right? Okay. Switching gears, library of parent functions. Determine which equations may be represented by the graph shown. There could be more than one correct answer. So all of these have base e. Now remember, the original e to the x graph is exponential growth because e is 2.7-ish. So in order to get it like this, I need to have a y-axis reflection. So definitely the graph needs to be e to the negative x to make it do this. So that's one thing, e to the negative x. So that rules out part A. So all these are e to the negative x. Now just go through each one. Like, it's hard to tell, but this looks like maybe it has, because all these have a 1, it looks like there's a horizontal asymptote at y equals 1. That would indicate a plus 1. So D definitely works. Check the other ones. The minus one's not going to work. That's going to drop it below the axis, so that's out. Would it work if we had both an x-axis and a y-axis reflection? So if I do this graph, but I do negative e to the negative x, that just takes this graph and flips it down here. And even if we shift it up 1, I don't think that's going to work, right? That's going to be going the wrong way. So there is only one correct answer for number 81. All right. Now this problem, the way it's set up is confusing. It says the table shows the population in millions of 5 countries in 2018, and then the projected populations, or like predicted populations for 2030 based on on our Census Bureau. Find the exponential growth or decay model. So now because again, we haven't done like how to solve this in terms of E or how to make it base E. So I'm not really fitting it into like e to a power, which is okay for what we're doing now and for what we'll need to do for AP. But the confusing part is we're used to putting data in a whole column in our table at once, but you're doing this for each country. So take a look at what I did here. So I want to get an equation for Japan to come up with a model, and I want to use the model to predict 2045. So first, give yourself an equation for Japan. So it says use 18 for 2018. So I used 18 and 30 here. So let's do this. Stat, edit. Oh, I still have it. Okay, 18 and then 30. And then what were the two populations for Japan? In 2018, it was 126.2. And in 2030, it's projected to be 120.8. Without getting an equation, you can tell if this is growth or decay. Is the population projected to go up or down? It's projected to go down. So I know it's a decay model. And rather than setting things equal here, I just used my calculator. So I'm going to do stat calc, and we want exponential regression. So go toward the bottom here. It's option 0, exponential regression. L1 and L2, store your equation in Y1 and calculate. So I wrote this down. Remember, when we do regression, we don't round our decimals at all when we write out our model. We want the whole thing. And we store it in Y1 so that it's not rounded. Predict the population in 2045. So now I want the calculator to tell me Y1 of 45. And it tells me this. Now this I can round my final answer to 3 places. And remember, the label is that this is a representation of the number of millions of people for that country. The other way that I know this is decay, maybe I didn't say, you're just given an equation and you don't have the table to look at. Remember, if the base number is less than 1, then that means that you have exponential decay. And if it's greater than 1, it's going to be growth. So I did that for each one. So now if I want to set up Canada, I still have 18 and 30, but now I'm using I'm using Canada's population. So 35.9 and 38.6. All right. And then I can do stat, calc. It was option 0. Store it again in Y1. You see how this could get a little tedious, right? And then I wrote down that equation. And then again, remember, you can just do I don't have it on my screen anymore, but you can say second enter, and it'll call that up again. Okay, so rounded to 3 places, that's my answer in millions for Canada. Or again, you can just keep doing Y1 of 45. So I did that for each one. Why are we doing so many? It's tedious, whatever, because again, you need to practice this. Some of you don't ever actually type it into your calculator for yourself, and then you're confused why you don't know how to do it on test day. So, if that sounds familiar to you, then please take the time to do all of these. If it feels tedious, great. That means you know how to do it. All right. Part B, you can see that the population for each country is changing at a different rate. The rate that it's changing is the base number, right? Because the first number just represents the initial population that we're looking at in 2000, I guess, in year 0 for this. So what constant in the equation is determined by these different rates? Discuss the relationship between the different rates and the magnitude of the constant. So what is that asking? So again, I just said it. It's the base number that dictates how quickly that you're growing or decaying the population, right? And think about this. This is like a percentage of what you had. So we're saying, okay, we're going to take roughly 99% of the population, and that's how much it's going to decrease each year. Excuse me. So it's going to decrease by about 1% each year. This one has a little bit over 100% by 0.006, so less than 1% increase. So what you're looking at is the base number dictates how quickly the population is increasing or decreasing. And then the farther above 1 that base number is, the faster that population is growing. So Philippines is growing the fastest. And then the decrease, the further from 1 that the value is, so the lower the base number is, the faster that's decreasing, right? So Japan has the lowest base number out of all of these. So it's farther from 100%, right? So it's decreasing the fastest. All right, what about this one? A conservation organization releases 100 animals of an endangered species into a game preserve. The organization believes that the preserve has a carrying capacity of 1,000 animals. What does that mean? It's like an upper limit. In my classroom, I have, 28 desks or something. So my carrying capacity, if we're going by desks, is 28 for this room, right? Once we get past that, sorry, we can't hold you anymore. So this preserve is not big enough to hold any more than 1,000 animals. The growth of the herd will follow this logistic curve. So what is a logistic curve? We'll talk more about this later in this chapter, but it's a curve that when you graph it looks like this. All right. So P is the population as we see it, and T is measured in months. So part A, what is the population after 5 months? That's easy. That's find P of 5. Use your calculator to do it. And because the follow-up questions involve graphing this, instead of typing this on our home screen, let's go ahead and get it into the y equals. Now, if your calculator has this function, remember, you can set up a fraction so you don't have as many parentheses. You can do alpha y equals to set up a fraction. If you don't have that option, you just need to make sure that you put parentheses around the denominator. So it'll be like 1,000 divided by parentheses, whatever. Okay, so let me type this in. I'm going to use the fraction thing. So it's 1,000 on top. Bottom is 1 plus 9 e to the negative 0.1656x. I'm being careful about that because I don't want to mistype it. All right, so what is y1 of 5? 202.745. 202.745. Now, we're talking about animals, and it doesn't tell us to round to the nearest whole, but I like to do that. So basically, we're saying about 203. It doesn't say what it is, so I'm just going to call them animals. After how many months will the population reach 500? So now we're saying the population is 500. Set that equal to 1,000 over 1 plus 9 e to the negative 0.1656t. Again, I have not gone through how to solve this algebraically. We will do that later in the chapter, but on the AP exam as well, if you're allowed to use a calculator, just use a calculator. We do this in calculus too. This is a case where I had a professor who said a lazy mathematician is a smart mathematician. That's only in reference to this. Know what you're allowed to do. If you can just use a graphing calculator, let's just fit this window. So now, what do I guess about the window? So when I plugged in 5 points, I got 202. We're looking for 500. So maybe we'll guess that the window is, let's do 1 year, 12 months, and see how that goes. And if I'm wrong, then I'll change it. So, all right, so I can see the 500, but I can't see the intersection. And the calculator, I don't think it'll find the intersection if it's not on your screen. Okay, so I got an error. So let's change the window. Let's go out to 2 years, 24 months. Zoom fit. There we go. All right, so I can find that intersection point, and this time it won't give me an error. There we go, 13.268. So I believe I have this in a screenshot here. Oh, wait a minute. I have a slightly different number, so let me see which one of these is right. Let me double check how I typed this in. Negative 0.1656x. So I think there's a good chance I might have had a typo here. So, okay. Let's fix the key while we're in here. Boop, boop, boop. Screenshot that. Delete you. Put this back on here. Copy. Paste. All right, there we go. Okay, so my answer for T is slightly different than what I originally had. How many months? 13.268 months. That's about how long we're estimating it will take based on the model to get to 500 animals. Also note, this is a calculus thing. When you're halfway to your carrying capacity, halfway to your upper limit, that should be a point of inflection. So, and it looks like it is, point of inflection. All right, part D says use the graph to determine, part C was graph. Okay, so boom, done. Part C and part B's answer is down there. Part D says use the graph to determine the values of P at which the horizontal asymptotes occur. So I don't think that we really need the graph for this. We can think about this logically. The number of animals can't be negative, so y equals 0 needs to be a horizontal asymptote. And then the carrying capacity, we're told, is 1,000. So there's got to be a ceiling at 1,000. Now, my graph as I have it does not really show much of this, but if I bump this window out, let's let it go negative. And let's go like 3 years, I don't know. Zoom fit that. So maybe I'll go further out on the right. Oops. Oh, I changed the scale. Whoops. Here we go. Zoom fit. There we go. That's a little bit better. So see how it's flattening out here. It's flattening here. If I hit trace and I go out to the right, I should see that I'm starting to get values that are pretty close to approaching 1,000. If I could bump it out more, I would. Okay, so we know that. So yeah, identify the asymptote that's the most relevant in the context of the problem. So most relevant, I would say p equals 1,000 or y equals 1,000. And that's because we're not going to have zero animals. They're interested in making sure that they don't hit their limit, or if they have too many, they're going to have to move animals to another preserve. So p equals 1,000 is the most relevant since they're tracking that population growth over time. All right, that was the last problem in the homework. If you're having calculator issues or need help with any of this, please let me know and come into office.